Here we have a Data Precision Model 1350 digital multimeter. It seems pretty cheap and nasty, but Data Precision is a respected brand, I believe. And if you came with an instruction manual, it's got specifications, how to use it, calibration procedure, troubleshooting, theory of operation, parts list, and most importantly, the schematic. So, let's turn it on. And all we get is +1, and it doesn't matter what we do. That gives us something. How did I get that? So clearly not well. Open it up, I guess. Now, I found an ad from Physics Today, March 1979, which has an ad for this beast. Data Precision brings you the DMM you didn't think you could afford. Blah 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 blah. $169 back in 1979, so that's a fair whack, isn't it? Now, any industrial or educational organisation, even a home hobbyist, can afford an outstanding laboratory precision instrument. Costs less, delivers more. Neat, eh? Okay, let's have a look inside of it. So it looks like just these 4 screws will release the case halves. I'll take the top 2 off and see if I can get the lid off. And yes, the lid comes off after those 2 screws are removed. And not a lot in there. ICL 7107. The only chip by the look of it. Really, the only chip. Oh no, there's a couple down there. Presumably talking to these LED drivers, talking to that display. So I guess the thing to check is power supply voltages. I shall look RTFM to find out where to test. Now, to get to the test points, you have to take off the bottom cover as well, which has a shield, and bottom looks like that. There's a spring thing to make contact with the shield there, and the front panel, I mean, these are stiff, ugly wires. It's really got a cheap and nasty feel to it, this thing, but little plastic nuts on here, as they call them. Which allows the front panel to come off so we can see what's under there. I'll zoom in a touch. Okay, main chip is the Intersil ICL 7107, and then there's 4 7404 driver chips. Well, that's easy if it's there the problem. There's one other chip, a TL082. One part that doesn't look that cheap and nasty is this thin film divider thing on a glass substrate. The rest of it looks pretty ordinary though. The test points are on the bottom, apparently. Oh yeah, there we go. All in large friendly numbers. 2, 3, 4, 5. And we'll get to that later. First we'll just check the power supply. Presumably these voltages are meant to be tested with respect to ground, and presumably that's what that earth clip is. Now the power supply is a bit of a strange one. There's four-way rectification that goes into this negative 5-volt regulator, and there's half-wave regulation to come up with this negative supply. But that is not ground. The common is actually V+, because the output of the minus 5-volt regulator, that is the digital return, and it goes to the bottom shield in test point 3. That's why I've got 0 volts measuring from test point 3 to the shield, because they're connected together. As it says here, the voltages are measured with respect to V+. I didn't see that back in the manual, so let's look for these voltages with respect to that, which can be found on the positive side of this big capacitor C16. Right, the negative of my multimeter is connected to the positive of C16 here, which is the V+ line. So now look for these voltages over here. So yeah, they've labelled that wrong. Yeah, they've labelled this wrong. That's pin 2 there, and pin 3 is the output. So we should have on the shield, test point 3, with respect to V+, minus 5 volts, and I think that's what we had, test point 3. Yeah, minus a bit high. Duh. Staring right in front of me. It's only when I chased the components on the other side that I found test point 1. Minus 12.5 volts. Right, voltages from the top. Analog ground, which is test point 5. 0 volts, so something wrong there. Digital ground, which is test point 3. Minus 5.5 volts, a bit high, or a bit too negative. Z1A pin 1 is up here and goes to test point 4. Test point 4, minus 4.8 volts, should be minus 7.5, so that's too not negative enough. And Z7 pin 3, minus 12, so a bit high. I've covered the exposed 240 volt stuff just with insulation tape for the moment, and on the bottom. I'll do something more permanent perhaps later, but just for now, so I don't give myself a boot. I've pulled out the ICL 7107 because I just got this gut feeling that it's the cause of the problem, because there's not much else to go wrong, is there? The voltage reference is this diode here. It's here on the schematic, a 1N4577, 6.4 volts, and the voltage on him, well, one side of him is connected to V+, and the other side obviously should be 6.4 volts lower than that, and it's not when this chip is in, but with the chip out it is, so I reckon that might be loading it down somehow. The 2.8 volts that's missing is still missing, the minus 2.8 volts at this point, this test point 4, sorry, test point 5, and it comes from, it's generated by this chip itself, from the negative supply, I believe. So it wasn't there with the chip in. Of course it's not there when the chip's out, but just more reason to suspect that chip. Now I can get one on eBay for less than $1, I think, but probably sus. But I can also get one locally, which is going to be a good one for only about $5 something. So I think I'll lash out and get one of those and see what happens. So we'll put this to bed for a few days till I get that chip and try it. Now, the voltages in here didn't make a lot of sense, and I'm pretty sure this main chip is involved in getting the 2.8 volts difference between analog common and digital common. And then I looked at my local supplier of old and wonderful parts, and they actually had the ICL 71007. It was only for $5. I thought, bugger it, I won't do anything else. I'll just get one of those and see what happens, and we're about to find out. There's the new one in place, here's the old one, and plug her in, switch on, and same shit. Oh well, so it's something else. I'll have to do some thinking. Actual investigation will be required. Quick and dirty didn't help. So I've replaced this ICL 7107 main chip, didn't help. So then I went to the other chip there, which is the TL082 op amp, and put it on a socket as well, and also no difference. I suspect that he might be the fault because he's involved in not having the right voltage at test point 4, but that was wrong thinking, as it turns out. Now, I know that electrolytic capacitors are the main cause of failure in most repair work of old gear, but I don't do a lot of repair work. Most of my troubleshooting involves my own projects where I'm typically using new parts, and therefore electrolytic capacitors aren't likely to fail, and it's more likely a semiconductor that I've burnt out while I've been mucking about. So I'm a bit too quick to jump to the conclusion of playing with replacing semiconductors, which is what I did with these two chips. Because this is so old, I should have started looking at capacitors. And the problem with this thing was that this analog ground should be 2.8 volts different from the digital ground, and that 2.8 volts comes from is generated internally in the ICL 7107, but it was, these two lines were equal, not separated by 2.8 volts. And if we look here, C8, capacitor between the +5 and analog ground. So I thought, what if he's gone short circuit? And it's this little dude up here. So I pulled him out and let's test him. Testing capacitor C8. .6 ohms. It's a short circuit. Now this is a reshoot because I lost the earlier footage. First time I did it was actually less than half an ohm resistance, but it's certainly not a capacitor anymore. And you can see there's no obvious damage to it. It's not leaking, it's not bloated, but it's not a capacitor either. Let's replace him. There's his mate, also 100 mic 10 volts and 120, so he's good. And the larger one, also 100 microfarads but 35 volts, and good as well, but I'm going to replace them. I won't bother with the big one. Maybe I should, but I probably won't. So they've all been replaced now. They were all 100 microfarads. The two little ones were 10 volts and the big one was 35 volts. These are 50 volt 100 microfarads. Time's marched on, so they're smaller than they used to be in those days, but let's see what happens when we turn it on now. That's better, isn't it? It's better. Let's try fooling around with some ranges. That's on volts, ohms, overload. That's the signal we were getting before, but now only on ohms. Milliamps, back to 0. AC or DC. A lot of difference. But by the way, this cap here is looking a bit tired. The capacitor for AC input, I'll probably replace him too. And I probably will replace this one as well, because it's only 16 volts. You know, might be sailing a bit close to the wind. I should have something lying around that'll make a good substitute for that. Alright, let's stick some volts in and see what happens. So on the volts range, 10 volts, and I'll just connect 6 volts from some batteries onto there, and 6.38. Could be right, might not be, don't know. I'll have to obviously calibrate this thing again. Let's try just this resistor. I'm not sure what resistance it is. On ohms, it's 270 ohms, 0.27k. So that looks like she's working. I've replaced these, of course, and I've also replaced this guy because 16 volts was sailing a bit close to the wind, I reckon, so I've replaced it with a 35 volt capacitor, still 2200 microfarads, and in keeping with the trend over the years, it's smaller than the lower voltage version that it replaces. This guy here, 0.1 microfarad 1000 volt mylar capacitor or polyester, seems a little bit harder to replace, although he looks a bit discoloured. I think I might just leave him there unless, or I'll eventually get something, but no rush to change that one. I think it's okay, I haven't tested it, but I will. So what I need to do obviously is recheck all those voltages, see that they're now within spec, and calibrate it according to the instructions in the manual, and then I think I should have a reasonably good meter. It's still only a, what is it, 3.5 digits. It's not high precision resolution by any means, but it might be high precision. I said it looked like a bit cheap and nasty. It has got a few things in its favour. For a start, it's got the precision resistor network for the voltage divider on the inputs. Although it's using a general purpose analog to digital converter and display driver, it's surrounded that by a precise current regulated Zener diode, which is this stuff up here. So there's the Zener. So it's got a precision current running through it, so that gives it a nice precision voltage, which we've got precision resistors providing the reference voltage to the ADC, and that also supplies a nice precise power supply voltage to the ADC. Furthermore, this chip, this ICL 7107, is perfectly capable of driving this display itself, but that would cause heating, and the heating would depend on what was being, how many digits were being displayed or how many segments were being displayed. So they've eliminated that problem by having these displays driven by these 7404 hex inverters down here, keeping the heating out of the ADD converter, which further improves its stability. So they've done a few things, although it's a pretty cheap plastic case, but yeah, it could well be quite a good multimeter. We shall see. Right, just checking those voltages on the test points again, which are approximate voltages with respect to V+, and V+ is available at test point 2. So, meter, test point 2, now test point 1 should be minus 12 volts, which is here. Okay, now I'm going to turn it on. Test point 1 should be minus 12 volts, 11.8 is good. Test point 3 should be 5 volts, minus 5 volts, correct. Test point 4 should be minus 7.5 volts, correct, close enough. And test point 5, which is the digital ground, sorry, no, it's the analog ground, should be minus 2.8 volts below, and it close enough there. That was test point 5 there. So I'm measuring, well, we're measuring across that capacitor that's been replaced, and rather than a short circuit, we've now got a capacitor, so things are good. Okay, I think I'll just clean up the case and put it back together. And finally, I've replaced the AC coupling capacitor with this guy down here. Cost about $4.50, that thing. So all in all, I've spent about, including this chip, maybe. So I spent about $12 on this on parts, and only paid $5 for it in the beginning. So it's still under $20, and it's a working multimeter now. So I think that was good value. And there she is with the front panel cleaned up. One small stuff up there, but we won't go into that, will we? And there we have it. Right, here we've got the Data Precision and Hewlett Packard. They've both been warmed up for an hour or so. Sticking 10 volt reference into it. And if we look at this, if we rounded that up to 4 digits, that would be 10.01. So that's pretty close, 10 millivolts out, maybe 20. Probably well within spec. I guess I could improve it by going through the calibration procedure, but I won't bother with that right now. The other thing I'll try is I've got a 10k resistance over there. Let's see if it agrees on that. And 10k, it reckons is 10k. So that seems pretty good. Yeah, so a nice little meter. Good name, Data Precision. Yeah, I hope you enjoyed that. If you did, give it a thumbs up and subscribe if you'd like to see more of this sort of stuff. And catch you later.